What's up, guys? It's the Big C here coming at you live from the recliner again with exponential modeling today. Read along with me at the top here. Just says exponential functions are very important in modeling a variety of real world phenomena because certain things either increase or decrease by fixed percentages. So that's what it's all about today, talking about percentage growth as opposed to linear growth over time. So right off the bat here, what do we got? We're putting money in a savings account that receives 5% interest per year. So we're adding 5% of the amount of money we have. Now, once we add 5%, we have more money. So 5% next year is a bigger amount that we're adding. And this is why this is not linear growth. This is exponential growth. So we're starting with, we call this an initial deposit. This is going to be the A value every time because this is when time equals 0. So this is essentially the y-intercept. Okay, how much will the savings account increase by over the course of the year? Well, it's going to increase by 5%, but a little review here. 5% is 5/100ths, which is equivalent to 1/20th, but then back to 5/100ths. This is why we write it in decimal form with 0 in front, because that's your tenths place, hundredths place, 5/100ths. So 5% of 400, you can calculate a number of ways. Simplest way would probably just be to take 400, multiply it by 0.05 and get 20 bucks. So we're adding 20 bucks onto our original investment. And we have $420 now. All right, now we want to shortcut that. We don't want to have to get 20 and add it to the 400. We want to just get to the 420. So we're going to multiply 400 by 1.05 and we're going to get right to 420. Why does this work? Well, 100% of 400 is 400, and 5% of 400 is 20. So when we add those together, we get 105% of 420. Oh, sorry, of 400. Okay. Part D, how much is in the account after 2 years and 10 years? Well, what we need to realize there is that for the 2-year amount, we're literally just going to take 400, multiply it by 1.05, get 420, and multiply that by 1.05 again, which is equivalent to, and this is important moving forward, 400 times 1.05 squared. So that's going to get us 441. Go ahead and test those out. Make sure that you understand, or you don't just take my word for it that they're equal. But that's the idea there, so that I don't have to write 10 1.05s. And I can just jump right to 1.05 to the 10th, and there will be $651.56 in the account after 10 years. Okay. So then in general, an equation for how much is in the savings account over time. Notice I'm using the variables they asked me to use. S would be the amount in the savings account, T would be time. Here's my initial investment. Here's my 105% in decimal form to the T power. Okay, now we want to determine how long it'll take for the initial investment to double. Well, double 400, that's 800 bucks. So that's our goal. 800 bucks. And we're just going to guess and check. The question is, when does our 400 times 1.05 to the T equal 800? So go nuts with your guesses. You could pause it and try to figure it out yourself, but spoiler alert, it's between the 14th and 15th year. So it's somewhere in year 14. I got 791, 97, and 831, 57. So it will take just over 14 years. So somewhere in year 15. For the investment to double. Okay. Big takeaway here is that this is not unique to this scenario. This is your general guide for how to create an exponential model, an equation, or a function for a function that's growing by a percentage. This 1 plus p, or p is the percentage. So in our case, it was 5%. And q0, that's just the quantity, the amount at time 0. So that was 400. When you add 1 and 5% in decimal form, which is 0.05, you get 1.05. So you're literally just anything that's increasing by a percentage, convert it to decimal form, add 1 to it, and you've got your base rate. Okay, moving on. Let's see. So now, okay, we're going to use that knowledge to build an exponential model here. We got an initial investment of 250 bucks and an interest rate of 3%. It's got to be this guy. Okay, again, it's literally just 100% plus 3% is 103%, but then convert it to decimal form. Okay. Let's see. Okay, now we're decreasing. Okay, so instead of starting with 100 and adding, we're starting with 100 and subtracting. So 100% minus 10% is 90%. But again, these equations have to go in decimal form. You can use 0.9 or 0.90. Here's 100% minus 25% is 75%. So we use 0.75 in our model. And 100% minus 0.5% is going to be 99.5%, which is 0.995 in decimal form. So these would go here in a decreasing equation. And here is one. Population of a town is decreasing by 4% per year, and it started with 12,500 residents. And so we're going to subtract 4%. Nope, common mistake. 4% is 0.04, 40% is 0.4. Let's see, so that would be our equation. Well, we just have to do 1 minus 0.04, which is going to be 0.96. And we're doing this for 10 years. Went to Desmos to fire that up. And by the way, I linked that at the top of the previous page in OneNote. But here's Desmos. Here's where I calculated that. Got 8,310.4 people. And so choice 4 is our answer. Cool. Well, our last page today, we're making a graph. And what are we dealing with here? Stock price of Wind Power Incorporated is increasing at 4% a week, and its initial value is 20 bucks. Durable Energy depreciating, which is losing money, decreasing in value at a rate of 11% a week. That was starting at 120 bucks a share. So Here's how we're going to build their equations. Let's see. Initial amount going up by 4% a week. Initial amount going down by 11% a week. I think I'll color code these though. So let's go. All right. 100 minus 11 is 89. There's where 0.89 comes from. Okay, so I draft these on Desmos first because it's just, I gotta figure out an appropriate scale to use here to be able to show everything they're looking for. They want a well-labeled graph, so we need, which equation is which, each function's y-intercept, and the point of intersection. So, fairly easy to do on Desmos. The key is that you can mess with your scale by pinching and zooming. Uh, so long as we can see both y-intercepts though, and the point of intersection, we're good. So I took that and then transferred it to paper, and I'll do that here now. We're going to put the stock prices on the right, on the left, sorry, on the y-axis. And you should always put your units in parentheses. We're going to put the time in weeks on the y-axis. And then if you ever have trouble coming up with a great title, just say y-axis over x-axis, because essentially we're kind of looking at slope, even though these are curved functions. We're looking at rates of change over time and finding a tipping point. So I labeled this tipping point between two stocks over time. To fit everybody in, I had to go and make this 120, and then realized, okay, 1, 2, 3, 4, 5. That would be 30, 1, 2, 3, 4, 5. That would be 60, 1, 2, 3, 4, 5. That would be 90. And let's see, for time and weeks, we could actually just count by ones. We're good to go here. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And 20. Cool. They intersect here, so the very important point here at 11.5, comma 31.4. Most important point on the graph for sure. We got to eyeball that it's about there. And we got to get everything to intersect there. Y-intercept time. The one that's rising begins at 20. So this is counting by, we got 5 notches here going up to 30. So these are 6 each. So that's 12, that's 18. So 20 is a little above that. And I also found one more fairly perfect point here, 5 comma 24-ish. So I'm going to mark that and use that to create like a curve for this W function. Now we're so zoomed out here that it's barely going to look curved. It almost looks linear. And since they intersect there and continue to rise, that's kind of the main focal point here, is when do they change over from one being more valuable than the other. So I'm going to leave it at that for now. And in the interest of time, just get this baby on here. There's your y-intercept for the g function. And I may have to erase just to get this intersect better. Yeah. And I'm running out of time, but I could perfect this a little bit more if necessary. G, and this is W. And looks like we pulled it off. Miss you guys. Hope you're well. We'll be in touch. Hope to see you soon. Take care.